Hi students, have a nice day. In this section we are going to discuss about the kinetic theory of gases. The macroscopic behavior of gases described by Boyle's law, Charles' law and Avogadro law. As we know these laws, Boyle's law explains variation of pressure versus volume at a constant temperature. Charles' law explains variation of volume and temperature with at a constant pressure, and Avogadro law, which describes the number of molecules or number of moles with respect to volume. To provide an explanation for uniformity of general behavior of the different gases, to provide an explanation for the uniformity of general behavior of different gases, Bernoulli proposed a theory called kinetic theory of gases, and later it was modified by Maxwell, Boltzmann and Clausius. Okay, let's discuss the important postulates of kinetic theory of gases. The first one is about the gas molecules. All gases are made up of extremely small, large number of particles called molecules. Okay, so the first point is all the gases are made up of large number of extremely small particles called molecules. The first point is based on the particles, that is called molecule. The molecules are in constant rapid random movements. Okay. The second point is the molecules are in constant rapid random movements. Rapid random movements. Random motion or movement in all possible directions. Okay, in all possible direction means there is no direction in all direction the gas molecules move, and during this collision or during this movement they collide with each other and also the walls of the container. So second postulate is based on the movement of gas molecules. Okay, the gas molecules are in constant rapid random movements in all possible directions. During this motion, they collide with each other and also they collide with the walls of the container. Okay, then next point is the collisions are perfectly elastic. Okay, the molecular collisions are perfectly elastic. That means they collide and just bounce back. Okay, they collide with each other and bounce back. The total energy of the gas molecules are constant. They transfer energy between the gas molecules. The total energy is constant. That means the molecular collisions are perfectly elastic. And the fourth point. So the third point is about the molecular motion. The movement are perfectly elastic. Perfectly elastic. Okay, perfectly elastic. And the fourth point is the pressure is exerted by the gas molecule is due to the collision of gases on the walls of the container. The pressure exerted by the gas molecule is due to the collision of gas molecules on the walls of the container. Okay, as we know that pressure is force per unit area. In a unit area, the gas molecules exert a pressure. Okay, the pressure is force per unit area. And the pressure of the gas is due to the collision of gas molecules on the walls of the container. Okay, yes. Then fifth point. So fourth point is pressure. Pressure is due to collision of gas on the walls of the container. Walls of container. And the fifth point is, okay, the fifth point, there is no intermolecular attractive force between the gas molecules. Okay, no intermolecular attractive force. No forces of attraction. Okay, are you clear? There is no intermolecular forces between the gas molecules. That means they just collide and bounce back. No attractive force between the gas molecule. Are you clear? Yes. And the sixth point based on the gravity. Gravity has no effect on the movement of gas molecules. Okay, the sixth point, gravity. Gravity has no effect. Gravity has no effect on the movement of gaseous molecules. Okay, then another point is, a very important point is, the volume of the gas molecule is negligible as compared to the volume of the gas. Please listen. Volume of the gas molecule is negligible as compared to the volume of the gas. The gas molecule occupied a small volume, and that volume is negligible as compared to the volume of the gas molecule. Okay, the seventh point is based on the volume. Volume of the gas molecule is negligible as compared to the volume of the gases. Okay, the next is based on the temperature. The average kinetic energy. The average kinetic energy of gas molecule is directly proportional to the absolute temperature. Okay, so the eighth point is based on the temperature. Temperature is average kinetic energy, or kinetic energy is directly proportional to temperature. So what is temperature? The degree of measure of hotness or coldness. That temperature is directly proportional to the average kinetic energy, because different molecules have a different speed. Okay, not all molecules have same speed. Some molecules is having higher speed, some other molecules with lower speed. That's why a large number of gaseous molecule in the gaseous system. That's why we take average kinetic energy. So these are the important postulates of kinetic theory of gases. Yes, next we discuss the behavior of real gases. Gas obeys ideal gas equation PV is equal to nRT at all temperature and pressure is called ideal gas. Okay, this we know that. The gases obeys ideal gas equation PV is equal to nRT at all temperatures and pressure is called ideal gas. Real gases behaves or the behavior of real gases is different from the ideal gas. Real gas deviate from the ideal behavior. And this deviation we will discuss. So behavior of real gas, the real gases deviate from the ideal behavior. And that's why the gases are called non-ideal gases. Real gases are also known as non-ideal gases. Why? Real gases deviate from the ideal behavior. Real gases approach ideal behavior at a low pressure and a high temperature. When the real gases behaves ideally at a very low pressure and a high temperature, real gases behaves ideally. As we know that ideal gas behaves Boyle's law, Charles' law and Avogadro law. So Boyle studies pressure volume variation. Okay, pressure volume variation. The pressure and the volume. Its pressure decreases, volume increases, and in vice versa, volume decreases, pressure increases. Also we study PV is equal to constant. PV is a constant. And the plot or graph PV versus pressure. Okay. PV versus pressure is a straight line parallel to the x-axis, that is pressure axis. Are you clear? These things we discussed. PV is a constant, that means PV versus pressure. Okay, the product of pressure and the volume versus pressure is a constant. So PV versus different pressures are a constant. The line is parallel to the x-axis or pressure axis. And this is the plot for ideal gas. Okay, so the straight line which represents the ideal gas. Real gases deviate from this behavior. For example, hydrogen and helium. Hydrogen is deviate from the ideal behavior. Okay, hydrogen is deviate from the ideal behavior. And then next is helium. Helium also deviate from the ideal behavior. And some other gases, for example, methane and carbon dioxide. Okay, methane and carbon dioxide, the PV versus P initially decreases. Okay, initially it is decreases and then increases. This is the plot for carbon monoxide. And the other is methane. Methane also first decreases then increases. Are you clear? Yes. Once again I explain. In the case of Boyle's law, the pressure versus volume. Okay, the pressure versus volume is a parabola. Okay, it's a slanting or a curved line. Okay, it's a curved line. This means volume increases, pressure decreases. Volume of the gas increases, pressure decreases at a constant temperature. And also we discussed the PV. PV is a constant. So PV constant means there is no change in the PV values with a different pressures. And the plot is we made PV versus pressure. The straight line is parallel to the x-axis or pressure axis. And that is the plot for ideal gas. Okay, you please understand these things. This is the plot for ideal gas. But real gases, H2, CO, CO2, methane, helium, argon, nitrogen, oxygen. These are real gases. These real gases deviate from the ideal behavior. In this case, hydrogen and the helium, they deviate from the ideal behavior. When pressure increases, the PV also increases. Okay, when pressure increases, the pressure volume increases. So such deviations are called positive deviation. Positive deviation. So for helium and hydrogen, the deviation is positive. Okay? Yes. Then in the case of carbon monoxide, methane, carbon dioxide, oxygen, like that, the PV decreases when pressure increases. Okay, when pressure increases, PV decreases and reaching a minimum value. Okay, reaching a minimum value, then it is increases. Okay, in the case of methane, that's the case of carbon monoxide. In the case of methane, the same trend we can observe. Pressure increases, PV decreases, and reaching a minimum, it will increases. Okay, so this is the deviation of real gases from the ideal behavior. And the second is negative deviation. Negative deviation. First thing is, first deviation is positive deviation, and the second deviation is negative deviation. Okay, so real gases deviate from the ideal behavior. And why this deviation from the ideal behavior? Kinetic theory proposed some postulates for the behavior of gases. And the deviation is explained by two faulty assumptions, by taking two faulty assumptions. Okay, the first faulty assumption is there is no intermolecular forces between the gas molecules. That is not hold good. That means it is faulty. At a very high pressure and low volume. Okay, at a high pressure and at a low volume. Pressure increases, volume decreases. The gas molecules attracts each other. There is intermolecular forces of attraction. Okay. Kinetic theory proposed that there is no intermolecular forces of attraction between the gas molecules. So there is a question, why the gas tend to liquefy and then to solid? When the gas is compressed, okay, when the gas is compressed on cooling, the gas molecules tend to liquefy. Also it is solidify. Okay, I think you heard about dry ice, solid CO2. Okay, solid carbon dioxide is called dry ice. So why the gas tended to liquefy? There is no answer by kinetic theory of gases. So the gas is compressed at a low temperature. The gas molecules attract each other. At a high pressure, the volume decreases. In that situation, the gas molecules tend to attract and then it is liquefied. Okay, so at a higher pressure is high pressure and low volume, also low temperature. Okay, at a high pressure and lower the volume or lower the temperature, the gas molecules attracts and then it tends to liquefy. That's the explanation, the deviation of the real gases from the ideal behavior. And the second faulty assumption is the volume of the gas molecule is negligible as compared to the volume of the gases or total volume. It is also not true. Okay, at a high pressure and a lower volume. Okay, suppose the gas is kept in a volume V. This is volume V. The gas molecules are kept. And remember that the gas molecules are in random movements. Constant random movements. And during this movement, they collide with each other. Also collide with the walls of the container. Okay, there is large space in that volume V. When the volume decreases by increasing the pressure, what happens? The volume of the gas is low. In that situation, when the volume is large and low pressure, the gas molecules are far away. Okay, the gas molecules are far away. There is no attractive force. But at a high pressure and lower volume, by applying the pressure, the volume decreases. In that situation, the volume occupied by the gas molecule is comparable. Okay, the volume occupied by the gas molecule is comparable with the volume of the gas. So, two faulty assumptions made by kinetic theory of gases is the deviation from the ideal behavior. Are you clear? First is there is no intermolecular forces of attraction between the gas molecules, and at a high pressure and a low volume there is intermolecular forces of attraction. There should be intermolecular forces of attraction, and that's why they attract each other, hence tend to liquefy and then solidify. So kinetic theory made a wrong proposal. And the second one is the volume occupied by the gas molecule is negligible as compared to the volume of the gas. Here, at a high pressure and a low volume, the volume occupied by the gas molecule is comparable, and that also a faulty assumption. Are you clear? Okay, let's wind up this section. You go through the postulates of kinetic theory of gases and the behavior of real gases, the deviation of real gases from the ideal behavior. In the next section, we will discuss about the van der Waals equation, van der Waals forces, and the deviation of real gases is expressed in terms of compressibility factor. Okay? Thank you.